what are some patterns you saw about either polar molecules or non-polar molecules with these pictures we drew? Rachel?
All the polar ones have brighter colors, so I was thinking that maybe that means that their bond and friendship was stronger than the non-polar one.
Good conclusion. Have a smiley face for that. Other conclusions?
Ones that were more positively or negatively charged were polar, but the ones that were like more even were non-polar.
Perfect. Okay. For those of you that didn't catch this from the simulation, the colors were signifying charges. Red signified negative. Yep, negatively charged. Blue was signifying positively charged. And the deeper or brighter the color, the more negative or more positive it is. So can you say that one more time, Jerem?
So the more negative or positively charged it is, then it's polar. So like if it's really positively charged, then it's polar. But if it's more in the middle and it's not really charged, then it's negative. I mean, it's non-polar.
Perfect. Have a smiley face fact. Any other, I heard similar themes. I heard like the non-polar ones were all kind of the grayish ones or the dim ones. But that's what polarity is polarity. Think of the word polar like the north and south pole, okay? When a molecule is polar, it has a positive side and it has a negative side. When something is non-polar, it doesn't really have either. It might be completely gray, it might have a little bit, but there's not a definite pole one way or the other. Hence the name non-polar as not poling, okay? Now, with this concept of polarity, can anyone think of something else in our world, in our life that we use that has positive and negative sides to it? Say it again, Melody. Magnets. Have a smiley face. So what polarity does is it turns our molecules into little magnets. Now I do quotation marks very particularly here because they aren't the same as a magnet. But they have a magnetic force because one side is positive and one side is negative. Hence, their friendship with other ones is stronger because they also have a positive and negative force. So that is the overall theme as we look at this unit, is the reason why something does what it does is because how strong or weak that positive and negative force is. Okay? Go ahead and open up your pink packet here and let's write some things down. Jackson, can I hit play on that camera?
Yeah.
Yes. I meant to, but then I couldn't remember if I actually did it. Okay, so number one, some definitions here to fill in. Okay. Yeah, sorry, I missed you. Did I get you one? Oh, I was like walking around putting them down while you were working, but I might have missed it.
Where are we writing the definition? Where are we writing the definition?
Okay, let me match up here. Okay, this is not matching up like I want it to. Sorry, one second. Okay, here we go. This should match up now. Does that match? Yeah,
We did not get pink.
I missed you too. Yeah, I would probably miss something.
Here you go, problem solved. Just kidding. Everyone else. One more?
Okay, so a polar bond is a bond between atoms of two different elements, tends to be polar. Now, like Jared pointed out, a polar molecule has a positive side and a negative side. Okay? What pieces inside an atom, so atoms are made up of protons, neutrons, and electrons. Okay? What pieces inside the atom can affect its positive or negativity?
electrons and protons.
So electrons or protons. Now, when it comes to a molecule, it's all about the electrons, because the protons don't move. But the electrons are moving because they're being shared, right? When we draw our Lewis structures and you draw that little line between them, you're saying, hey, they're sharing electrons. What happens is it's not always shared equally. Sometimes one of the atoms is pulling on the electrons more than the other. So it causes this shift in positive and negative charge. That shift in electrons is all about electronegativity, which we've got to think back to, like, I think it was unit 2 where we did this trend. Okay, if you want to make a side note to this, the trend for electronegativity, so here's like a periodic table, okay? The trend for electronegativity went like this. That these ones have high electronegativity, and these ones have very low electronegativity. In a sense, electronegativity will tell you who is winning the tug of war. Now, the way we draw that in chemistry is we use what is known right here. This is known as a dipole arrow. The dipole arrow shows you the directions that the electrons are being pulled. In this case, since chlorine is further to that corner than hydrogen is, the electrons are going in this direction. They're still sharing. It's not ionic where it steals it. It's just not being shared equally. Okay, it's probably maybe like when your mom says, hey, share this treat with your sibling, and you have your cookie and you break it in half, but it doesn't break equally, and then you give your sibling the bigger piece, because that's the kind of person you are.
What? Ever give your sibling the bigger piece?
I'm trying to give you the benefit of the doubt, people. But you can still say you shared, right? But it's just not shared equally, okay? In terms of our electrostatic clouds that we drew before, the dipole arrow points to the side that would be red, because that's the negatively charged side. That's why on the end of the dipole arrow right here is a plus sign. It's showing, hey, this side of the molecule is positive, and this side of the molecule is negative. Okay? Once again, it always points in the direction with the one with the higher electronegativity. So when we determine whether a molecule is polar or not, what we're looking for is, hey, is there a definite negative and positive side? Or is it all pretty much balanced? Okay, so there's two main pieces that will affect the polarity of the molecule. Cool. So let's say, for example, on this molecule, that B has a higher electronegativity than A. So take your pencil and let's draw arrows to show that pole of the electron. So we're going to draw an arrow going out like this way, and that way. So we do have three different tug of wars going on here when you look at each individual bond. But if you look at the molecule as a whole, the tug of war is canceling each other out. One way in which you can do this, and this is what we'll kind of do on our assignment here. Let me grab my arrows just so I can move them easier. Okay? I'm not sure if any of you, has anyone ever learned about vectors before in math yet? Maybe I haven't got that point? Okay. Anyways, anyone seen Despicable Me 2 or 1?
Physics.
Is he 1?
Yes.
Despicable Me 1. Right? Evil guy, his name is Vector. What's his catchphrase?
Oh, I forgot.
Anyone
With
know?
direction and magnitude.
Okay.
You have to look at
How do you remember that? Okay, thank you for that. So, in a vector, it's all about the direction it's going and the strength at which it's pulling. In this case, the three arrows are the exact same strength because they're all the same element. Hypothetically here, if this was a different element, then maybe it wouldn't have as strong a pull. right? So that's why I drew the arrow shorter. But for our case, they're all the same. With vectors, if they cancel each other out, the molecule is nonpolar. Okay? The way you determine that vectors cancel is you take the arrows in the direction they are, and then you put them together with the tails pointing to the head of another. Okay, so notice I'm not going to change the way they are, I'm just going to move them side by side. So I'm going to point this head to that tail, this head to that tail, and they cancel each other out. Okay, so I didn't rotate them, I just kind of slid them so I could see, hey look, they're canceling out, and so this molecule we would say is not polar, it's nonpolar. So one of the things that we'll say a nonpolar molecule is if it's perfectly symmetrical. Okay, molecules that are perfectly symmetrical are not polar because the tug of wars cancel out. Now keep in mind, if you want to make a side note, you've got to think in 3D space for symmetry here. Okay, you've got to think about what these things look like in 3D. Got to be careful with your Lewis structures because your Lewis structures might not show the 3D shape. One of the main things that makes a molecule not symmetrical, let's pick here for example, let's get our water right here. Why is water bent? What's keeping those hydrogens from going straight?
It has
The lone pair.
Perfect. We have the lone pairs, we have the ghost pushing them away. So one of the things that you often can look for determining polarity is a lone pair. Okay, if it has a lone pair on it, it prevents the two dipoles from canceling each other out. So notice, so here's my dipoles. Okay, now I'm going to line up head of one to tail of the other. Notice, what is the overall direction the arrows are going? Up. So we have an overall dipole shift in this direction, meaning this side of the molecule is going to be negative, and that side of the molecule is going to be positive. Questions so far? Okay, so two things that we can look for are asymmetric shape or asymmetrical atoms. Once again, we're going to do another example, quite a few examples of this. But okay, any questions right now? Okay, let me pass this out.
Well, we have to know and determine like where the arrows are supposed to be pointing at some point.
Yes. Yes, so that's what we're going to practice right now. So our main goal right now is that if I give you a molecule, you can tell me if that molecule is polar or nonpolar and the direction that it's going, if it's polar. Okay, so we're going to work on this first worksheet in our homework packet here together. I'm going to do the first few with you, and then we'll have you try some with your table buddies. Okay, so here are the steps you're going to take on this assignment. Okay? Everyone have paper? Okay, step one, if you look at the instructions, it says for each of the given molecules, draw a dipole arrow on the image for each polar bond. Okay? So we need to figure out, do the arrows go like this, or do they go like that? So how do I determine which way the arrow's going starting?
Which one has more electrons?
So close. Which one has more electronegativity? So whichever one is closer to this corner will pull harder. So looking at O or C.
Oxygen.
Perfect. So take your pencil on the image and draw two arrows, dipole out like so. Because you have an oxygen on this side, you have an
Why
oxygen on
would
that
it be-
side.
So it'd be pointing to the oxygen because of like how it increases, like it's
Yes.
pointing to what.
Yep, oxygen has a higher electronegativity, so between the tug of war, it always wins.
Okay.
With carbon at least. Questions so far? Okay, so step one is you should have some arrows drawn in that first box with the image. Okay? Step two is we're going to combine the arrows to see if they cancel. So in this case, if I put head to tail, we get that. So draw this in that second column. That's the combined arrow picture. So I'm lining them up to see if they cancel. Okay, now based off what we've seen so far, give me a thumbs up if you think this molecule is polar, or a thumbs down if you think it's non-polar.
Because it's not because if it's red, then it wouldn't be.
If you're giving me a thumbs down, have a smiley face, you're correct. This is a non-polar molecule. Questions so far? Okay, give me a thumbs up if you want to do some more together. Give me a thumbs down if you're ready to try it with your table buddy. So thumbs up with me, thumbs down, I want to try my own. Okay, we're about 50-50.
Do we need the name of it?
Yes, so what's that shape called?
Linear?
Yep. So that's just kind of reviewing last unit a little bit. So if you need to pull those notes out again, you can. Okay, let's do a few more together. Let's do water here.
Guys.
Okay, so first step, look at the periodic table. Who wins the tug of war, oxygen or hydrogen? Oxygen, so draw two arrows. Like so. Okay, so first step is to draw the arrows on the picture. Second step is to combine the arrows in the next box. Okay, so think of as just like I'm doing on the board, think of you're just gonna slide them over, but line up the head with the tail. Okay, so I'm just gonna slide this, keeping the pointing the same. So that's what you should have in the next box. Okay. Thumbs up, thumbs down, polar or non-polar. If you're saying polar, have another smiley face. And notice there's one other piece in the directions. If you identify it's polar, we're going to add an overall dipole arrow to show the direction. So in this case, it's like we said before, the overall direction is, in a sense, up. So draw a big arrow upwards on your water molecule, showing, hey, all the electrons are going this way. Yeah,
So
Rachel.
what is like the official clue to determine if it's polar or non-polar?
If you have an overall shift in electrons one way, it's polar.
Okay,
If it doesn't shift one way because they kind of cancel each other out, it's non-polar.
got it.
Does that help?
Okay, yeah.
Okay, you want to do? I'll do one more for those that want to follow along with me. I think this is the next one on your paper. Okay. All right. So we got two different molecules, three different atoms here. So first, look at this tug of war between H and C. Who wins? Okay. Between C and N, who wins? Okay, so there's your arrows. Now in this sense, when you combine them, they're already kind of written combined because the head points to a tail. So thumbs up, thumbs down, polar or non-polar. Once again, polar means the electrons are all going one way. Non-polar means they're balanced out. Very good. Definitely very polar. And this one's, the overall dipole would be pretty much how the arrows already are, but like so. Okay, as you work through the rest of these, I'll walk around, but all of these are also on the simulation. So after you do the problem, if you want to pull up the simulation and open up the electrostatic potential, if you identified it's polar, you should see a blue and a red side. If it's non-polar, once again, we should see that not so, or pretty balanced of colors, okay? All right, I'm going to give you a few minutes to work on this, and then we might cover one last thing. We'll kind of see where we get, but.
Oh,